A split second, the Big Bang, and the whole universe was born.
In the blink of an eye, literally, so much can happen that it would blow your mind.
How did we get here? And what is the universe made of?
The secret of creation, the secret of everything, is locked in that first second.
Technology stands on the brink of revealing what happened in the most important second of all time. In the beginning, there is nothing. No matter, no energy, not even empty space, because space itself doesn't exist. No time passes, because there's no such thing as time. From nowhere appears a fireball smaller than an atom. 10 trillion times hotter than the core of the sun. Everything that will become the universe explodes from a point millions of times smaller than a pinprick. Time begins. In 1 second, the blueprint for the entire cosmos is written. How it happened is the biggest mystery of all. Professor Lawrence Krauss has devoted his career to studying the first second after the Big Bang.
If we want to really understand our place in the universe, we have to go back to the very beginning and understand how it all came together.
Looking back to the instant of creation is a new idea. The theory of the Big Bang is widely accepted, but the concept is less than a century old.
But one of the things we have to put in perspective is how recent our understanding of the universe is. 80 years ago, the conventional wisdom in science was that the universe was static and eternal, had been around forever.
But this changes in 1929. At California's Mount Wilson Observatory, Edwin Hubble studies the light from galaxies. He observes that the farther the galaxy, the longer the wavelength of light it emits. Light waves stretch the more they travel, and stretching changes their wavelength. The same principle applies to sound waves. As a train approaches, the whistle's pitch rises. When it passes, the pitch lowers. As the train recedes, each sound wave has to travel farther than the last to reach your ear. The sound waves stretch, lowering the pitch. Something similar happens with light waves. If a galaxy is moving away from us, its light waves stretch, becoming longer and redder. It's called red shifting.
When we look at visible light, there's red at one end of the spectrum and blue at the other. Red radiation is the long wavelength radiation of visible light, whereas blue radiation is the short wavelengths. And as we look at the universe, we see the radiation from distant stars literally stretching so that the light gets redder. And the farther away we look, the redder the light is.
Galaxies around us have shifted to this red light.
We look out in all directions at distant galaxies. They're all moving away from us.
Nearly all galaxies are receding at 1,000,000 miles an hour. If galaxies are speeding away from each other, at some point, they must have all been together. The universe is expanding outward from a single point. It's the first evidence that the universe had a beginning. Hubble's findings lead to a radical concept: the Big Bang theory. Scientists believe that in the first second after the Big Bang, the building blocks were created for every star and planet in the cosmos. To prove it, they first need a new way to tell time.
We are thinking of fractions of time smaller than we think about in any other area of human activity, and smaller fractions of time than a race car or a sprinter or anything else. And what we've learned is that more can happen in a fraction of a second, in a blink of an eye, than you can imagine. It would just blow your mind.
Hours, minutes, and seconds are the basis of modern life. But events after the Big Bang happen in fragments of time far smaller than a second. To analyze what happens, scientists use a new measure of time called Planck time. 1 Planck time equals 10 to the minus 43 seconds. That's a decimal point, 42 zeros, and then a 1. It's an unimaginably small amount of time. Yet in this first tiny beat of Planck time, something happens that shapes the next 13.7 billion years. Out of the fireball, the 4 fundamental forces of nature form. Those forces underpin everything around us. Gravity is the reason stars and planets form. It rules the moon and tides and keeps us on the ground. Electromagnetism lights our cities, connects our phones, and runs our computers. And the 2 nuclear forces, strong and weak, bind the particles that make up our bodies and power the furnace of our sun. We're here because in the first second after the Big Bang, the 4 forces are created. Without them, the universe would be a featureless fog of radiation.
If there were no forces, nothing would happen. There'd be no television. There'd be no sports. There'd be no love, no hate, no human tragedy, all the things that make life worth living.
But in the first beat of Planck time, the 4 forces are still rolled into a single superforce. Gravity, nuclear, and electromagnetic forces have not yet divided. Physicist Michio Kaku studies how the forces split apart.
I like to think of it as a crystal, a beautiful symmetrical crystal, all the forces unified in their elegant simplicity at the beginning of time.
As our cosmic clock takes one more tick of Planck time, the tiny fireball universe expands. The 4 forces start to break apart. It's like rapidly cooling a super hot crystal. Cracks form.
It began to shatter into 4 pieces. The first piece to break off was gravity. Then the nuclear forces began to split off. And finally, we have this fragmented jewel of what used to be the superforce.
Those 4 fragments are still at work. Gravity keeps Earth in orbit. Nuclear forces make sunshine. And electromagnetic radiation, the light that bathes our planet. We're just fractions of a second into our journey, and already the foundations of our world are forming. The fireball universe. Still smaller than an atom, and 1,000 trillion degrees. To discover how the universe expands, scientists use telescopes so powerful they can see the past. When astrophysicist David Spergel looks up, he sees history.
As we look out in space, we look back in time. Light travels at a finite speed. So the light we see from the sun takes about 8 minutes to get here. We see the sun not as it is, but as it was 8 minutes ago. We look out the night sky, we see the nearby stars. They might be 10 or 20 light years away. We see them as they were 10 or 20 years ago.
The Big Bang was so powerful and so hot, remnants of that heat still survive. The heat began as superhot X-ray radiation. As it stretched and cooled, it became visible light, shifting from blue to red, then becoming microwaves, and finally radio waves. This faint radiation shines down on Earth all the time. It's called cosmic microwave background radiation, or CMB.
The cosmic microwave background is the echo of creation itself. It's the embers, the afterglow of the original shock wave that created the universe. If we had microwave eyes that could see microwave radiation, then every night we would see the Big Bang coming out. Looking at the heavens, we would actually see an explosion.
More than 13 billion years later, we have a way to see this cosmic glow with the naked eye.
You take your TV set, switch it between channels. A couple percent of the static that you see on your TV screen is radiation from the Big Bang.
This cosmic radiation is a direct connection to the Big Bang. It also reveals the universe entered a new phase, less than a trillionth of a second after its creation. Cosmic radiation is the key to discovering what happens next. A few beats of Planck time tick by on our cosmic clock, and the fireball universe is transformed. One instant, the universe is billions of times smaller than an atom. The next, it inflates to the size of a baseball, growing more in this moment than in all the 13.7 billion years to come. Scientists call this rapid expansion inflation. And the evidence survives in the cosmic radiation left over from the Big Bang. Like static on your television, this cosmic radiation seems so constant and so even, it presents scientists with a puzzle.
When we measure the cosmic microwave background in that direction, its temperature is identical to its temperature in that direction. It's the same everywhere.
The only explanation is the universe inflates countless times faster than the speed of light. Inflation expands the fireball universe evenly, like a balloon blowing up, with a phenomenal breath of energy.
I try to imagine compressing a spring. I push it closer and closer and closer together so it's smaller and smaller and smaller, and I've stored a tremendous amount of energy in that spring, and when I let it go, it bursts out. And that stored energy drove an exponential expansion of space.
But if the entire universe is uniform from the first second after the Big Bang onward, how did the galaxies form? Planets and stars begin as clusters of particles. Over time, these particles of matter clump together under the force of gravity to form a dense mass. Earth began as a ball of particles that clumped together through friction and gravity. The sun that sustains life on Earth started out as a cloud of gas and dust. How did these clusters form in the first place? The early universe should be lumpy, not even. To link the formation of stars and planets all the way back to the first second after the Big Bang, NASA scientists like David Spergel developed the Wilkinson Microwave Anisotropy Probe, or WMAP, a satellite mission to measure the temperature of cosmic radiation in more detail than ever before.
While this radiation is everywhere, it's very faint. And to observe it in great detail across the whole sky, you want to get away from the Earth and any interfering sources of radiation.
7, igniters armed, green board, 5, 4,
NASA launches the probe in 2001.
main engine start, and liftoff of the Delta II rocket with the MAP spacecraft, exploring the past and future of our universe.
It could produce the best ever snapshot of the universe in its first second.
The launch was incredibly exciting, tense, An exciting moment to see it go up and then realize it was working.
WMAP sits 1 million miles from Earth. It's so sensitive, it can measure the temperature of cosmic radiation within 1/1,000,000th of a degree. For 5 years, WMAP analyzes the sky in minute detail.
It sits there with the Earth and Sun always behind it, staring out into space. The satellite's spinning very rapidly. It covers about a third of the sky every hour, spinning and making maps of the leftover radiation.
WMAP tracks the Earth as it orbits the Sun and scans the temperature of the whole sky. It generates detailed temperature maps like this one, and it reveals something remarkable. The blue and red patches on this map of the entire sky are tiny ripples in temperature.
The little blue regions represent regions that are a few tens of thousands of degrees colder. Red regions are a little bit hotter, so you're seeing tiny variations in temperature across the sky.
WMAP looks back over 13 billion years. As the universe evolves, these tiny ripples develop into clusters of particles that get bigger and bigger under the force of gravity, becoming just dense enough to trigger stars and galaxies to form.
I mean, it really was what I think we all dream of when we go into science. Looking at things that no one's looked at before, learning really exciting things about fundamental questions. Questions like, what's the universe made of? What happened in its first moments?
This is a map of how the universe looked in the first second after the Big Bang. The template for today's vast cosmos.
When the picture of the cosmic microwave background radiation first came out, the press said, the face of God. Well, let's be real. It's not the face of God. What it really is a baby picture of the infant universe. So the discovery of the cosmic microwave background radiation ranks as one of the greatest discoveries in all of science.
Less than 1/1,000,000th of a second after the Big Bang, the fireball universe rapidly expands. Now an ultra-hot globe big enough to sit in the palm of your hand, the universe is seething with energy and radiation. But as the palm-sized universe expands and cools, something new starts to form. Only a fraction of a second after the Big Bang, and the destiny of the universe is already mapped out. The sun burns because of forces forged more than 13 billion years ago. The stars and planets form from the way the universe rapidly expands. Science can trace everything we see today back to the first second of creation. But we're here because of what happens in the next few beats of Planck time. The universe is flooded with the building blocks of matter. So far on our cosmic clock, the early universe is nothing but energy. How did pure energy turn into matter? Everything around you is made of matter. What you're sitting on, the air you breathe, the whole planet is made of matter, and matter is made of atoms. And in the first second after the Big Bang, the ingredients for atoms are created. How matter appeared mystified scientists until 1905, when Albert Einstein comes up with our most famous equation. E equals mc squared. Einstein's equation tells us that energy, E, and mass, m, are different forms of the same thing. Matter and energy are interchangeable. Some scientists later used this equation to create the most destructive weapon in history, the atomic bomb. It offers a clue to what happened in the first second. In a nuclear explosion, particles of matter are ripped apart to produce an enormous amount of energy. During the Big Bang, the exact opposite happens. An enormous amount of energy turns into matter. Einstein's equation prompts a conclusion. As the baby universe expands and cools, the pure energy of the Big Bang converts into the particles of matter that make us. We're only a fragment of a second into our journey. The first particles of matter appear. The universe is 1,000,000 times hotter than at the core of the sun, still far too hot for particles of matter to bond and form atoms. Scientists face a puzzle. What is this early state of matter like? And how does it become the protons and neutrons that form every atom in the universe?
Atoms were impossible. Think of putting an ice cube in a steam bath. The ice cube would melt immediately. You cannot have ice cubes in a steam bath.
You can see the proof in a block of ice. When water is cold enough, it's a solid. Warm it, and you get a liquid. Heat liquid water, and it boils away into a gas, water vapor. Superheat the gas, and the energy pumped in rips the atoms apart. Likewise, the universe in the first second is so hot, only the building blocks of atoms can exist.
If you were to journey into the early seconds of the universe, literally you would disintegrate. You would literally fall apart, and even the debris, the nuclei of your bodies, they too would fly apart into subatomic particles. There would be nothing left of your body.
There's only one way to see these super hot building blocks of matter in the first second after the Big Bang. Scientists must recreate conditions of the Big Bang itself.
The inside of a star is measured in tens of millions of degrees, but the Big Bang was measured in trillions upon trillions of degrees. So we have no way to simulate the instant of creation other than with a particle accelerator. By slamming protons into other protons, we can create temperatures not seen since the beginning of the universe itself. So particle accelerators are the only game in town when you talk about simulating Genesis.
This is Brookhaven National Laboratory in Long Island, home to the Relativistic Heavy Ion Collider, or RHIC, a 2.5-mile ring designed to smash the nuclei of gold atoms at nearly the speed of light.
With the particle accelerator, you slam subatomic particles together. As a consequence, we get a tremendous shower of debris, and then we want to make sense out of it. We want to know what's inside that collision.
The energy of the collision is colossal. On a small scale, it reproduces the embryonic universe in the first second. How? By ripping nuclei into the protons and neutrons they're made from. The energy is even enough to rip the protons and neutrons apart. Inside, scientists discover the building blocks of matter, tiny particles called quarks. But they're so small and move so fast, they're hard to track. If scientists can figure out how quarks behave, they'll unlock the secret of matter itself. What they find could revolutionize medicine and relaunch the space program. The project starts in 2000. Colliding nuclei creates a chaotic spray of particles. It takes 5 years to analyze the data. The results come in 2005. They're shocking.
We were expecting to find a gas when we slammed gold nuclei into each other. So the shock was, it wasn't a gas at all. We found that it's more like a liquid. So this came quite a shock, because now when we begin to simulate the early universe, we have to get rid of this mental picture of a gas of subatomic particles. Now we know it's more like a liquid, literally like a soup.
When matter first appears in the universe, the quarks are so dense and so energized that the entire universe is like a liquid. The universe went from a glowing ball of energy to quark soup in less than a blink of an eye. The liquid universe is hot, dense, and violent, flooded with tiny particles in constant vigorous interaction. As our cosmic clock reaches a millionth of a second, the universe continues to expand and cool. It grows from the size of a baseball to the size of our solar system. Matter has materialized from pure energy. Without matter, none of us would be here. And in that first second, that very nearly happens. Something comes close to destroying all matter in the universe. Armageddon is brewing. A split second after the Big Bang, and the universe is flooded with the building blocks of atoms. These tiny particles of matter must survive in a battleground. Everything around us is made of matter formed from the energy released by the Big Bang. Every molecule, every atom, every quark. How we end up with a universe that consists of so much matter is one of our biggest questions. The particle accelerator may reveal the answer. When the first second is recreated, two types of matter are produced in equal parts. One is the type of matter we see around us. The other is its opposite, antimatter. Dr. Tara Shears explains they're two sides of the same coin.
This apple is made of matter. We know that every matter particle in the universe has an antimatter partner that was created in the Big Bang. Now, antimatter looks similar to normal matter, but not quite. In fact, it looks like the mirror reflection of matter. So an anti-apple looks like this.
If the universe was made of antimatter, it would essentially look identical to how it looks today. You and I would be made of antimatter, and anti-lovers would sit in anti-cars looking up at an anti-moon at night making anti-love, and it would be largely the same.
But matter and antimatter are mortal enemies. They can't coexist.
When we have a matter particle meeting an antimatter particle of the same type, then they annihilate, they explode together, they destroy each other. All the energy that the matter and antimatter particle have goes into one large explosion of huge, tremendous energy.
Fractions of a second after the Big Bang and the future of the universe is at stake, matter and antimatter are locked in a battle to the death. A millionth of a second after the Big Bang, and a battle rages. When matter and antimatter clash, the result is explosive. Just one apple-sized clump of matter hitting its antimatter equivalent would release as much energy as a 10-megaton nuclear bomb.
If you could go back to the really early universe just after the Big Bang, you'd find yourself in this seething mass of matter and antimatter annihilating each other. You'd find yourself in the middle of this cosmic battle between both sides, caught in the crossfire, if you like.
With all the particles in a super-dense liquid state, matter and antimatter quickly meet and destroy each other. Since they're created in equal numbers, and every matter particle that hits an antiparticle is annihilated, all matter should be destroyed as soon as it's created.
all the matter would have eventually found the antimatter and they would have annihilated, producing pure radiation. And we'd now have a universe. I was going to say we'd now be living in a universe of pure radiation, but we wouldn't be living in such a universe because we wouldn't be here. There'd be nothing but radiation.
But the universe is full of matter. How did it defeat antimatter? It's one of science's great mysteries. One theory is that antimatter is less stable and decays more quickly, creating a tiny imbalance between matter and antimatter. This tiny imbalance eventually allows matter to overwhelm antimatter. Whatever the truth, something happens just after the Big Bang that tips the balance in favor of matter.
And the whole battle stopped at that point, and what was left was a very small amount of matter. And it's that small amount of matter that makes the universe that we live in now. That means that we're the leftovers of this battle. We're the dregs. We're what's left when everybody else had finished.
The dregs go on to form everything around us. From the ground beneath our feet to the most distant galaxy. As the cosmic clock nears the end of the first second, nature's four forces have split off from the single superforce. The winner of the matter and antimatter war has been decided, and the subtle ripples in temperature that stretch across the universe mean that over the next billion years, gravity gathers clumps of matter to form galaxies. But one mystery remains, and it's a big one. We know how the building blocks of matter form, but we don't know what gives everything in the universe substance. We know so much about the first second, but a piece of the puzzle is missing. What gives everything in the universe mass? Mass makes it tough to get something moving, and makes it hard to stop. When we're pulled down to Earth, gravity is acting on our mass. On the Moon, gravity is weaker, so astronauts move slower, but their mass is the same as back on Earth. Even if an object weighs nothing, it still has mass. Something must have been created in the first second to give particles mass, but scientists haven't found it.
We have this hole. We have this missing piece. The centerpiece of this whole picture is what happened during that first second of creation. If you know that, then you can, quote, read the mind of God, as Albert Einstein used to say.
Mass is the very backbone of life.
If there were no mass, the universe would consist entirely of radiation, and nothing could bind together to form objects like you or I, or any of the things that appears to make the universe interesting. It would be a diffuse universe full of radiation, but very, very boring.
Discover how mass develops in the first second, and you uncover the root of life. If scientists can't find what gives particles their mass, that first second will remain an enigma. Our journey is almost finished, but a piece of the puzzle is missing, and it stumped scientists for decades. Then in 1964, at Britain's University of Edinburgh, physicist Peter Higgs comes up with a groundbreaking theory. He suggests an invisible force field sweeps across the universe in the first second, giving particles their mass. It's become known as the Higgs field. When particles interact with it, they gain mass.
For example, if I take a car and that's run out of gas and I push it on the road, eventually I can push it and I can move it along. But if it runs into the mud, if I try and push it, it will suddenly seem heavier. I can't push it as hard. It'll act as if it's heavier. Well, we think that particles have mass for a similar reason. There's this Higgs field, And some particles interact with it more strongly than others. And the particles that interacted with it less strongly are easier to push, and therefore behave as if they're lighter. The particles that interact with it more strongly are harder to move and act as if they're heavier.
Like mud, the Higgs field sticks to everything. When particles enter the field, they gain mass. The more contact with the field, the more mass they gain. Scientists believe the Higgs field is carried by its own special particle. Journalists call it the God particle. Scientists call it the Higgs boson. They think identifying this particle could reveal how we got here. The math is good, but no particle accelerator was powerful enough to find the Higgs boson. Until now. Deep beneath the countryside in Geneva, Switzerland, is mankind's most expensive experiment, the Large Hadron Collider, or LHC. The world's biggest particle accelerator and the best shot at finding the missing Higgs.
We've got to see if the Higgs particle really exists. And that's why we have to build these mammoth accelerators, to see if we can understand the mechanism responsible for the existence of everything we think of as solid and heavy in the universe today.
It cost $10 billion, took 14 years to build, and involves the work of 7,000 scientists. This year, they switch it on. On a small scale, it will recreate conditions last seen over 13.7 billion years ago. An explosion so powerful, it will echo the Big Bang itself. If it works, scientists like David Evans could solve the last mysteries of matter.
Because we're pushing the frontiers of science, we have to also push the frontiers of technology. It is, as well as probably the biggest machine in the world, it is certainly the most complex machine in the world.
Over 300 feet underground runs a 16-mile circular pipe. Inside, two beams of protons, thinner than a human hair, are accelerated to almost the speed of light, 186,000 miles per second. The LHC will smash particles together 7 times harder than any other accelerator. 300 trillion protons fly around the pipe in opposite directions and collide in the heart of enormous detectors. Lawrence Krauss inspects one of these detectors, each the size of a 5-story building.
Here we are at what's been aptly described as being one of the Gothic cathedrals of the 21st century. This monstrous structure made of thousands of tons of steel, more iron than in the Eiffel Tower, with tens of thousands of miles of wire. All of this designed by thousands of physicists from hundreds of countries, speaking dozens of different languages, with the precision of perhaps a millionth of an inch, just to detect what happens inside there.
The LHC uses 4 of these giant detectors along the beam pipe. The one they hope will find the Higgs is called Atlas. Atlas is half the length of a football field and weighs as much as a nuclear sub. It can detect 1 billion collisions per second. When the protons collide, the impact is so titanic, in a split second, it will recreate matter as it was just after the Big Bang. A shower of fundamental particles, like quarks. Somewhere in the debris, they hope to find the elusive Higgs. But finding one particle in this firestorm is like finding a speck of gold on a beach. The Higgs is so tiny and so short-lived, the detector won't see it directly. Instead, they hope to capture the trail it leaves behind using the most high-tech cameras in the world.
When you look at a Skywriter, you see this gigantic plume of smoke, but where's the airplane? You never see the airplane. The airplane is too small to be seen. That's how we use detectors. Detectors cannot pick up the particle itself, but it can pick up the trail left over by the subatomic particle, and looking at the trail, we can determine what kind of particle it was and how fast it was moving.
The LHC will generate more data than any other instrument on the planet.
In a single second, the amount of information that's coming out of the collisions at the LHC that will be handled by these detectors is greater than the amount of information in all the libraries in all the countries in the world.
That data may hold the secret of mass, the missing piece in the universe's first second, and the doorway to the science of the future. To process all this information, the LHC uses the world's largest network of supercomputers. Even so, the search may take years to complete, but it's worth the wait. If it succeeds, the LHC could launch a new era in science. If it fails to find the Higgs and reveal how matter gets its mass, it will leave a hole in the riddle of the first second. New theories will have to be written, and more powerful experiments built.
Hey, I'm a realist. I realize that perhaps we'll find nothing. That could create a crisis in physics. It could stagnate all of physics if all of a sudden our machines are not powerful enough to unveil the next act, the next curtain, where we look at the next stage of matter and energy.
One thing they know, the LHC will take scientists closer to the Big Bang than ever before. It will reach back 13.7 billion years to recreate the very first second of the universe, the greatest second. Our cosmic clock takes its final beat of Planck time. The universe is 1 full second old. It's about 1,000 times the size of our solar system, and flooded with particles of matter, the raw material of everything around us. The universe is cool enough for the sea of quarks to bunch in threes, forming protons and neutrons. In the saga of the universe, this first chapter set the course of history.
The first second of the universe was an incredibly exciting and important time. During that first second, all the matter in the universe was made. All of the neutrons and protons were made. All the key components to make the universe today, we think were already in place. And then everything just evolved forward.
In the next few minutes, the universe cools enough for protons and neutrons to form the first atomic nucleus. 300,000 years later appears the first atom. In hundreds of millions of years, matter clumps to form the first stars. And in 1 billion years, galaxies like the Milky Way. More than 9 billion years after the Big Bang, Earth is born. One Big Bang, one single second. The genesis of everything.
By the time you've got to the end of 1 second, the rest of cosmic history is prescribed, including, ultimately, the future of the universe.
More than 12 billion years after the Big Bang, humans evolve. A species with the intellect to ask, how did we get here? And what is the universe made of? This year, science moves closer to discovering the answer. And the secret will lie in the first epic second.